Hi there! Today we're working on OSPF again. Understanding OSPF phases will make you leaps and bounds better at configuring and troubleshooting OSPF when something goes wrong. OSPF always breaks at a specific phase. So if you know what phase OSPF is currently in and what that phase is trying to accomplish, then you'll know where to troubleshoot without guessing. And the best part, we can watch these phases happen on the command line interface. I'll demonstrate how to use a debug command at the end of this video so that you'll be able to see exactly which phase OSPF process is failing in. We started to cover OSPF phases in the last video, so if you didn't catch that video, I suggest you pause here and go back and watch that first video. I'll link to it in the description so you can find it easily. For everyone else who watched the previous OSPF video, here we are back in our simple OSPF island using a point-to-point network. When we last left our island, our routers had begun exchanging hello packets. To review, we discussed two OSPF phases, init and two-way. There is one more phase that comes before these two, and it is down. The down state simply means no hello packets have been exchanged yet. These three states and the remaining four are called OSPF adjacencies. Learning these OSPF adjacency states is the point where I hope you are going to be bit by the OSPF spider and become the OSPF superhero that you didn't even know you wanted to be. I'm doing a dating app analogy for OSPF, these remaining phases. Full disclosure, I've never used a dating app. I never needed to, and they didn't exist when I was dating. And yes, I didn't say it didn't need to. They just didn't exist. And so yes, I realize this might be a little bit cringe coming from me as a mom to you as a student, but being a mom and being cringe are part of my job, so I feel it fits in with my whole persona. And as long as it gets you to remember the OSPF states, then the goal has been accomplished. So let's talk about dating the OSPF way. After we move from down to init and two-way, which as I said before we discussed in a previous video, we move into ExStart. You can think of ExStart as who leads the exchange. Deciding who will be the leader and who will be the follower takes place during the ExStart phase. Think of ExStart like a dating app moment where someone has to make the first move or the conversation goes nowhere. OSPF doesn't leave that to chance. The decision about who communicates first is made with the highest router ID. The router ID that is highest always becomes the leader, and then the lower router ID or IDs become the followers. During ExStart, the controlling router also selects an initial sequence number, which keeps the exchange organized and predictable. At this point, no topology has been exchanged yet. The routers are only agreeing on who leads and how the exchange will be organized. And honestly, if dating worked like OSPF, there would be fewer awkward silences and no question about who should respond and when. Okay, I'm going to take a little bit of a break here from the technical bit and address something that you're going to see in OSPF that's going to be uncomfortable. And I'm not even kidding. In ExStart, we talk about a leader and a follower, but you're going to see different terminology on the command line output. Frankly, in the late 1980s when OSPF was developed, this terminology wasn't acceptable then, and it isn't acceptable now. The terminology that's used in show commands and debug output is master and slave. That terminology was updated in 2023 and is now referred to as leader and follower much more appropriately. However, and this is important for your studies, you will see the terms master and slave in the command line interface output. I'm bringing it up now because I don't want you to be surprised or shocked by it, and I don't want it to dissuade you from continuing down your network engineering path. All right, now that you've been warned, we're going to get back to the technical side of things, which is much more fun to talk about. Okay, now we have moved on to exchange. So we're exchanging information. No, wait, we're not exchanging full amounts of information yet. During the exchange phase, routers send database description packets, DBDs. DBD packets contain summaries only, not full information. At this stage, the information exchanged is a high-level summary of what each router knows. Think of it as comparing story headlines, not the full story. If we're using our dating app analogy, the DBD packet is like seeing if you already know certain information about that person, and then deciding what you might want to ask later. You might look at their profile and say, oh, I can see they have a favorite color, but it's not listed. I don't know what it is. If you are missing information about their favorite color, you're going to note that down, and then you'll request it in the next phase. The goal of exchange isn't to exchange full amounts of data yet, even though it's in the title. No, it's to answer one question. Do you have information that I don't know yet? Once routers know the answer to that question, then they move on to the loading phase to request only the information that's missing. Here we are in the loading phase. This is where the actual information is exchanged. During loading, routers send link state requests. They say, send me the information I'm missing. That's a link state request. And the other router responds with a link state update to that request. And it says, here's the information you asked for. Each update is then confirmed with a link state acknowledgement. So this process repeats until no information is missing. If we go back to our dating app analogy here, yes, we're back to the dating app analogy. In dating terms, a link state request is like asking a follow-up question. I don't know your favorite color. What is it? And the link state update from the other router would be, oh, my favorite color is orange. And then the originating router would say, link state acknowledgement. All right, I received that information. Duly noted. Your favorite color is orange. I'll only send orange roses, whatever. You know, you get the idea. The goal of loading is simple. Transfer only the missing information and synchronize your databases. Once all the requested information has been exchanged and acknowledged, the routers move into the full state. We made it! Full state is the goal. Uh-oh, it looks like our OSPF hero may not have known that at first, but he appears to know that now. Well, our spider couple has successfully made it through every adjacency state and fully synchronized their link state databases. So let's move from cartoons to reality and see this on an actual Cisco router using a debug command. This is our logical router topology. In my lab, I'm using two Cisco 1921 routers connected using their serial 0/0/0 interfaces. OSPF is already configured on both routers. Router 1 has a router ID of 1.1.1.1, and router 2 has a router ID of 2.2.2.2. Here's a quick look at my physical lab setup. I'm connected to router 1 using a console cable that's directly going to my laptop. That means you'll be seeing the OSPF process from the follower's perspective. Remember, the router with the higher router ID takes the lead. So router 2.2.2.2 will be the leader. Here's a question for you. At what stage is the leader and follower determined? Well, let's take a look and find out. I'm going to start by entering the command debug IP OSPF adjacency. I'm using a shortcut here for the word adjacency. And notice nothing happens yet. That's because even though OSPF is configured, one of my interfaces is down because I unplugged it from the router. To force OSPF to walk through the states and show them in the debug output, I'll just plug that serial cable back in, and this will cause OSPF to restart the adjacency process. First, we see the serial interface come back up. Serial 0/0/0 is up. The P2P notation here tells us this is a point-to-point connection. This part is the interface coming online after I plugged it back in. It's not part of the OSPF process yet. Next, we see OSPF recognize the network. Network 10.0.0.0, area 0. At this point, we enter the init state. From there, the routers move into two-way communication. When routers enter two-way communication, that means that router 1 here has seen its own router ID of 1.1.1.1 listed in the hello packet that it received from router 2. We covered that in the previous OSPF video. ExStart happened very fast, and it's not explicitly shown here, and that's normal on a simple point-to-point network. Even though we don't clearly see ExStart scroll by, this is where the leader and follower decision is made based on the router IDs. And we can see here with our terminology that we discussed earlier, yes, we are the follower, and the other router, 2.2.2.2, with its higher router ID is the leader. After that decision is made, the routers move into the exchange state. We can see this happening here with a notification that a database description, DBD packet, has been sent. Remember, those DBD packets are just the headlines. It's not the actual full information exchange like the name would indicate. So what we are seeing here is just the summary of the link state advertisements that the other router has and that we may not know about yet. And here we can see an LSU containing an LSA, which is a link state advertisement being sent. That means we're now in the loading state. Again, loading is not explicitly listed here because we have such a very small network and the phases happen too quickly for even debug to catch all of the states in the output. But we know that loading is the stage where link state updates are received. So we know that this is the loading phase. Now we see the next step, which is full, indicating the transition from loading to full. We know at this point that our OSPF adjacency has fully formed and the link state databases are synchronized. This tells us that OSPF is functioning correctly. No spiders were harmed in the debugging of this network. You can see final OSPF states through various show commands, which we'll look at in a later video. But the debug command shows you the OSPF processes as they're happening. If OSPF gets stuck, the state that it gets stuck in will help you to determine where to begin troubleshooting. Thanks for joining me and my 2 OSPF love bugs this week. In the next OSPF video, we'll discuss even more interesting OSPF concepts. Probably not in the realm of dating, unless I can figure something out to keep these cute little love bugs around. I hope this made sense for you. And if it did, well then, we're winning. See you next time. Bye-bye.